Hi guys, good morning. I hope you guys are doing alright and had a good weekend and staying safe. So like I said, I'm gonna start recording the meeting because I figured out we could do that, and it might be helpful if you miss something and you can go back or listen to something or see something. You can see the whole meeting kind of as a screen cap presentation. Okay, so let's see where we are. Okay, so we're up to this point. We've done example 4.5, the direct connection example. We've done example 4.8 and 5.4, and those were all been due. These two were due today, and those two were previously due. And so try to get those in if you haven't into the discussions forum. And so make sure you get any spreadsheets or examples you haven't done yet before the midterm date, because you have to update the assignments grade at some point. All right, so what we're going to do today is example 5.6 and 5.5 and 5.6 in chapter 5. Okay, and I also found as a reference that might be useful if you don't have the textbook. If you click on the syllabus tab on your Blackboard, I put a PDF version of an older edition of the textbook, and it's got a lot of similarities, so you can look at that, and I'll kind of refer to it because it's easy to see. I can't really show you guys the textbook via WebEx, but we can look at this, and it's got the whole PDF version of an older textbook, and so we can look at that as some examples. Okay, so let's do example 5.5 and 5.6 if there's no additional questions. And so let's go to the Blackboard page. Okay, and so you want to open up the example 5.5, 5.6 if you don't have that already, and either have that as a reference or you can print it out if that's an option. Okay, there's a quick video on the shortest path concept. Which the videos will be optional kind of, but if you want some refresher on this idea, you can look at that quick video. It's on the link on the Word document. Okay, and we have a couple pretty short examples, and so the first one you want is the shortest path document or Excel file. We'll open that up first. Okay, so let me show you guys what this simple exercise is about, and if you look at, I can show you guys kind of from the older version of the textbook, the little synopsis. So it's this one, example 5.5. And so Maud Jenkins, a 90-year-old woman, is planning to walk across the state, east to west, to gain support for a political cause she favors. She wants to travel the shortest distance to get from City 1 to City 10 using the arcs or roads that we see in that figure that are set up in the Excel template. The number on the arcs are miles, and arcs with double-headed arrows indicate the travel is possible between, in both directions. And if there's just one arrow going one way, you can only go that direction that the arrow is pointing. And so we're going to decide what route mod should take to get from city 1 to city 10 in the shortest distance, right? Okay, so this little network model shows all the possible options, and these options are modeled in Excel. So she starts here at 1, and for example, she could 70 miles from city 1 to city 2, 56 miles from city 1 to city 4, and so on. So she can't do it all in one shot, but she can try to minimize or find the shortest distances to get from here to here, and that's what we're going to do, is minimize that walking distance. Okay, so we need the shortest path Excel file, and we need the steps, for example, 5.5, the shortest path, Word document. And so I'll just go from that. Okay, so first thing we have to do is set up our part of the cell is the inputs, decision variables, objective constraints, and then make some range names. Okay, and so this shows the exact problem that was modeled in that picture. Okay, all of these options are ways you can walk from one city to another in the distance. You can go from city 1 to city 2, 70 miles. You can go from city 6 to city 8, 52 miles. So these are all the options that she has to get from city 1, destination, city 10. Okay, so our objective will be that. And this little flow balance constraint is what you use for a shortest path model, because you're going to have something starting here that has to get to the destination. It doesn't always have to be a distance thing like this, but this is how you set it up, is you have like one thing that gets here, and then it gets received in the destination. Okay, so the distance block, those are inputs. We can color those light blue. Okay, so C5 to C39. Okay, the whole flow area, that is our decision variable range, so we can color that the light red color. D5 to D39. The objective is to minimize total distance, so that's our objective cell, D42. Okay, and our only constraints here are going to be just an equality constraint right here to show that the net outflow has to equal the required net outflow. So you can just put an equal sign starting in H5. And you just want an equal sign right there in all the cells from H5 to H14. So we'll specify that the net outflow has to equal the required net. The net outflow has to equal the required net outflow. Okay, so let's make a few range names. So we can do one for origin, destination, distance, and flow all together because they're right next to each other. So if you select A4 to D39, Alright, so you can make a range name for all four of those at once to have these names. There are four range names. Alright, you can make a range name for your total distance, A42 to B42. Alright, and then you want a range name for both sides of the flow balance constraint for net outflow. G4 to G14. And required net outflow I4 to I14. Alright, so these are your range names. You got destination, distance, flow, net outflow, origin, required net outflow, and total distance. So everybody got all these range names? Okay, so let's go on and try to decide the shortest distance for mod to walk. Okay, and so step one is to set up the arc list, which is already done. And so columns A and B show all the possible options for her to walk and the associated distance. Let's put some values in our decision variable range just so solver can solve that later. So you can just put ones, starting in D5 all the way down the red cells. So you can just put a 1 and a reading number in D5 to D39. Alright, so solver can solve that later. Okay, the step 2 is the net outflow. So starting here, you want to put in that formula, and this is similar to the one we did for the last meeting's exercise with the net outflow constraint. So step 5, put in that formula you see. Step 2, put in that formula you see in step 2. The sum if minus sum if formula. Okay, your formula here is equals sum if origin F5 flow minus sum if destination F5 flow. So you're getting the net of what comes out of the origin minus what goes into the destination, so that's the net. And you can see that the cell reference F5 is for node 1. And we can copy that formula down. Okay, so if you got this one, you can copy it down to just capture the rest of the nodes. So just double click the bottom right corner. Alright, so you can now it's changing the F reference all the way down to F14, which is exactly for node 10. Alright, the other part of step 2 is just to set up the right side of the required net outflow constraint. And so you can see all you have to do is put a 1 in the first one, and then zeros in between, and then a -1 in the final cell. So in I put a 1. In I14, put a -1. And then all the cells in between in that column, just put zeros. Okay, so for these shortest path models, you just want a 1 in the first one, then zeros in the middle, then a -1. And it just kind of sets it up because it's a zero-sum game. And so that way, the net has to be 0. So all these 1 here, 0 here, and then -1 here. Okay, step 3 is to calculate the objective, the total distance. So you can go down to your total distance to the yellow cell. Put in that formula for step 3. All right, so it equals sum product, distance comma flow. And so this is the same for all the network models that you see. Okay, no problem, Gonzalez. All right, so let's see, anytime she chooses the flow, if she chooses to walk that route, add the distance. So it's either 1 or nothing. So either she does this one and it's 70 miles, she does this one at 60, or she doesn't. So the sum of all the options is obviously the total distance. All right, so equals sum product distance flow. Okay, so now we're going to use the solver to minimize the shortest distance. And so we need anything else before we before we do the solver, or any help getting the solver? Okay, well let's run solver and see what the best option is to minimize this walking distance from C1 to C10. All right, so if you have the option, hopefully some of you do, is data solver. All right, so the objective is the total distance, so that's B42. Okay, so make sure you minimize that because she wants to walk the least amount of distance. Our only, the only thing we're changing in these problems for the shortest distance in the network for the flow cells. And so we just called that whole range flow. So you can just type in the range name, flow. Okay, we have that one constraint, and let's specify it. And we want to say the net outflow equals the required net outflow, just like it shows in the Excel file. So you can just do that. And first select the net outflow. All right, and change that inequality to an equal to, because it's got to be equal to. And then the right side of the constraint is the required net outflow range. Okay, so G5 to G14 equals I5 to I14. It should show that net outflow equals required net outflow when you hit OK. Okay, and then make sure you change that solving method to simplex LP because that makes it a linear programming option like we've been doing. Okay, so this is what your solver parameters should look like before we hit solve. Okay, your objective is total distance. You want to minimize that. You're changing just the flow. Your only constraint is net outflow equals required net outflow, and you want to make sure the solving method is simplex LP. Alright, so we can hit solve. Okay, so it looks like the shortest distance, total distance, is 198 miles. And so we can look at the route she chose. Hopefully some of you guys got that solution as well. Alright, so you can, I'm just going to highlight the options she chose just so you can see it. And so she chose to go from City 1 to City 4 and walk 56 miles. If there's a 1 in the flow, that means she chose it. Okay, then if we go down, you can see she went from City 4 to City 6, and that was 45 additional miles. And then finally she walked from City 6 to City 10, and that was her destination. Alright, so she chose these three routes, and you should probably see that all the distances summed to what we got in our solver objective, 56 plus 45 plus 97 should be 198. Okay, so a pretty simple model here, but it shows you the concept of shortest path that we can use for more advanced models. And so we have one more to do, but we're done with the shortest path one. Any questions, or do we need any repeating on this before we move on to the next example? Oh, question is, I'm sorry, I stepped away. Did you highlight them manually, or did you use conditional formatting? I just did it manually, but I suppose there's some conditional formatting I can use. Well, I know how to conditionally highlight the flows, but I'm not sure how to do the whole thing. Yeah, there's only three, so you can just highlight them. It doesn't really matter. It's just a reference. All right. So if we're good on this, you can close it, save it, and you're done with this one. This one goes right to the discussion forum for example 5.5, example 5.6. Okay, so we have two for today. They're both pretty short. We've already done one. They both go right here in discussion forum, example 5.5 and 5.6. And those are not due until next Monday. But just so you know, they're grouped together because they're both pretty short, or at least this one is pretty short. Okay, the other one we'll do, which is on the same Word document, and the steps is example 5.6, so you can open up the machine replacement Excel file template. Okay, and the PDF version of the older edition of the textbook has a nice description of this one. What we're going to do right now, example 5.6, which is equipment replacement at Van Buren Metals, and this will utilize the shortest path method, even though we're not actually doing distance here, but it works for all kinds of different concepts. And here we're trying to minimize cost for the life cycle of machine replacement. So here's what we're doing here. So Van Buren Metals is a manufacturing company that uses many large machines to work on metals. These machines require frequent maintenance because of wear and tear. And Van Buren finds that it's sometimes advantageous from a cost standpoint to replace machines that continue to maintain it. So once they get, just like cars or automobiles, at some point, if you keep going to the auto shop and it's like $2,000, at some point you got to turn in the car and get a new one. All right. So for one particular class of machines, the company has estimated the quarterly cost of maintenance, the salvage value, from reselling the old machine, and the cost to produce the new machine. All right. So we'll assume that the maintenance and salvage costs depend on the age of the machine. All right. So as they get older, it requires more wear and tear because they've done more. Things start to break or wear out. Okay, but it doesn't incorporate inflation, but it does incorporate the age of the machine. So the purchase cost of the new machine, $3,530. Maintenance cost of the machine in the first quarter is $100, and then it increases $65 each additional quarter because more things go wrong as you put more work or time in the machine. But you can salvage the machine after one quarter for $1,530, and then each quarter after that, the salvage value, what you can get back for it, just like if you traded an old car, you can get $1,530 after one quarter, or you lose another $110 each additional quarter. All right, so Van Buren wants to utilize or develop a strategy for purchasing machines over the next 5 years. And it says they have a policy that they never sell a machine that's less than 1 year old, so they have to keep it for at least 1 year. And they never keep it more than 3 years. So it's going to be quarterly. And so it's going to be the solution is going to be some total number of quarters to potentially keep this machine to minimize costs, somewhere in between 1 year and 3 years. Those are the boundaries. Okay, and then the machine at the beginning of the quarter is brand new. And so we're trying to develop, just like a path in general, like how long should we keep the machine for, and when should we get a new one to minimize costs. Okay, so let's find the optimal replacement strategy by using the shortest path method to solve this problem. Okay, so this is the spreadsheet we're going to be using for this one, and this is the machine replacement file. Okay, and you can see the inputs, which we're going to highlight light blue right now, and then I'll go through those. So we have the purchase cost, of $3,530, how much it costs to buy a machine. We have the maintenance cost. In the first quarter, it's $100, and then each additional quarter, it's an extra $65 because it gets more costly as the machine gets older. Okay, and then we have the salvage value. This is what you can sell the machine for if you want to replace it. So you can sell it for $1,530 after one quarter, and then that drops in value by $110 each additional quarter. So you lose a lot of value right away. It's almost dropped in half. Okay, so we'll develop the network ARPS and the maintenance costs, but the flow of this, the decision variable range for this problem is all the flows. And so there's quite a few of them, but we're only going to choose the optimal ones. But we got to highlight this whole range as a possible decision variable cell. So you can start with S14. All right, so this whole range, we're going to highlight light red. So I highlighted S14 all the way to S130. So those are all, that's the flow, the whole flow range that we're going to need to name as a range. So you can highlight S14 to S130 and just make that the light red decision variable color. Okay, and over here we have a similar type of balance constraint, and we're just going to show the only constraint in this sort of path model is that the net outflow has to equal the required. So you can just put an equal sign in here for now, starting with W14. And you can copy that equal sign all the way down this W column. Okay, so W14 to W34, you want an equal sign. Okay, and then just our objective is total cost, so we can make that the light or the highlight yellow color. Okay, so step, the first thing we have to do is we did the inputs, the decision variable range, and the constraints and the objectives. Now we're going to make some range names. And so there's a bunch, but they're all kind of grouped together. So let's start with origin, destination, and quarters to keep. We can do all those together and make 3 range names simultaneously. Alright, so if you select A13 to C130, let's make 3 range names like that. Alright, so we can make one for the salvage value, the purchase cost, the total cost, and the flow all together. Alright, so you can select, it's kind of a big range, but P13 to P13 to S130. Okay, then make the 4 range names for those. Okay, then we can use a range name for the both sides of the flow balance constraint, the net outflow. V13 to V34. And the required, which is X13 to X34. And I recall that we have a total cost range already, so we have to call this, let's call this total cost something else, because you can't have the same range name for 2 different ranges. So if you just click on V36, which is the objective, let's just go up to the name box and call this capital T, capital C. And it's the total cost, and just hit enter, because it's got to be separate from the other total cost. So that's total cost, or that's TC. Alright, so I made these ones, destination flow, net outflow, origin, purchase cost, orders to keep, required, salvage value, TC, and total cost. Alright, so total cost is that whole range, TC is the objective total cost. Alright, so we got all these range names. Okay, so let's start solving this machine replacement problem. Okay, step 1 is to put in the inputs, which have already been done right there. Step 2 is to put in the arcs, which have already been done. Right, all the origin and destination possibilities. And so this means, for example, you get the machine in the first quarter and keep it till the 5th, and so you kept it for 4 quarters. So these are all the options at which you can potentially keep the machine. Alright, and step 3, I believe, is already done, is the quarters to keep, and so that's just the difference between the values in column B and column A. And so you need the quarters to keep to calculate the cost and the maintenance cost and the salvage value. So that's just like 5 minus 1 is 4, 6 minus 1 is 5, and those have all been done through the whole quarters to keep column. Okay, so the big calculation here is the maintenance cost. And so you want to put in this formula for step 4. And we're going to copy it to the whole big range, the D range all the way to the O range. Okay, so when we put in this formula, And if we get it correctly, we can apply it to that whole range of cells. This is the formula for step 4. Yeah, name manager. Okay, you're welcome. Okay, starting in D14, put in that bulk formula for step 4, equals. Alright, let's see if we got this right. So it's equals if D $13 is greater than $C14, comma 0, comma $B $6 plus $B $7 times parentheses D $13 minus 1 and then double parentheses. Okay, and so let me hit enter and then I'll explain this one. Alright, so all we're doing here is calculating the maintenance cost based on how many quarters we kept it. So this tells you if this is the maintenance cost, so if D13-1 is bigger than 4, put it as 0, and so you know it's not. So the other case is, since it's less than, it puts in the maintenance cost. So the maintenance cost is D6, 100, plus 65 for each quarter. And so each additional quarter is the current quarter minus 1. So this is for the first quarter, and then this is for each additional quarter. If we have the machine in the current quarter, then this calculates the maintenance cost. So the first part of the argument is if we would have the machine. If we don't, then just put a 0. But if we're maintaining it, then it's calculating 100 plus 65 for each additional quarter that we kept. Okay, and this formula, make sure you have it correctly, can be applied to every single other cell in the maintenance cost range. Alright, so we got this formula. Okay, and now I'm going to grab the bottom right corner and drag it all the way from 1 to 12 like this. Alright, and we can also, since it's already selected like that, if you have D14 to O14, you can apply this formula all the way down to the, and I think if you just double click the bottom right corner, okay, yeah, it should apply the same correct formula and modify it based on the current order. But you want that same formula you type in this whole range, which would be D14 to O130. Alright, so you just copied and pasted the same exact formula that you put in D13 to the entire rest of the range for the maintenance costs in the respective port.
Hey, Professor,
Yeah.
I had a question on mine. I did the same thing from the 100 and I got the formula right, but for my 3 and 4, I got like 2 number signs, you know, just like the hashtag number symbols or whatever. I didn't get numbers put down. After that, it's all zeros.
Okay, so that probably means that either the formula's got a missing thing or it didn't copy correctly, because if you got the hashtag thing, that means it's not giving you an actual number. So
okay, and for after the 14, it's a capital O, not a 0.
Oh no, that's a 0.
Okay.
Yeah, that probably doesn't, because it's an if statement. So it says if this 0, otherwise do the thing after the 0.
Yeah, because I had the 0 before, and it still gave me that. Yeah, I got it now. Thank you so much.
It worked, the whole thing?
Yeah. Yeah, I got it.
Okay, so everybody got this whole range. The same formula was just applied to the whole range of D14 to O130. And as you'll see, if you specify the formula correctly, it'll look at the current order and determine the maintenance cost. So if you have a machine, it's just $100 from when you got it, and then another $65 for each additional quarter. And obviously, if you got rid of the machine, you're not paying maintenance on it because you don't have it anymore. Okay, so if we're getting that, let's go to step 5, which is the salvage value. You put in that formula you see in a P14. All right, so that formula is equals $V, $9 minus $V, $10 times P14 minus 1 in parentheses. Okay, so what this does is, let's see. All right, the salvage value after 1 quarter is, we know, 1530. You can see that with the blue highlight cell. And then each additional quarter, it's another 110. So this is the total salvage value of the machine that you have. So you can see that if you keep it for 4 quarters, it's going to be 1530 plus 110 plus 110 plus 110. All right, and this is all determined on how long you keep it. The longer you keep it, it's an extra 110 to maintain it. Okay, so if you got this formula, you can double click the bottom right corner and apply it down the whole P column. So you want that same exact formula in P14 to P130. And that should calculate the appropriate salvage value for each option, depending on how long you keep it. Okay, let me see. I got a question. All right, so I put a 0. All right. Okay, no problem. All right, so we got some private chat. I might have to edit that in the recording. I need to talk to my editor. All right, so let's go to the purchase cost, step 6. Alright, so this one's easy. In Q14, just reference the purchase cost. And so this should be equals $B, $4, and that's just the purchase cost is always the same, which is $3,530. Okay, so put that in there, equals $B, $4, double click the bottom right corner. And so you should see a 3540 in all the cells from Q14 to Q130, because if you buy the machine, it's always the same purchase price. Okay, so total cost, you can probably guess, is the maintenance cost, that's the purchase cost, and then if you salvage it, that's like a rebate. You get that back. So to specify in step 7, R14, put in that formula you see. Alright, equals sum of D14 to O14 minus P14 plus Q14. Okay, so this is pretty simple, but it's the sum of all the maintenance costs together. You gotta pay that, and then you also, if you salvage it, you minus that P14. So if there's a salvage value, that's like a rebate, but you gotta pay for the purchase cost. So it's your total cost is the purchase cost plus the maintenance cost minus any salvage value. Okay, and if you got that formula correct in R14, you can double click the bottom right corner and apply it down the whole total cost R column range. Alright, so that formula should be applied from R14 all the way to R130. Alright, step 8 is pretty simple, but I guess we haven't done it yet, is to put any trial values into the flow column, the decision variable range. Let's put ones in there for now. Alright, so the easiest way is just type in a 1 in S14, and then double click the bottom right corner to apply that 1 down the S column. Okay, so you just got a 1 in S14 to S130. Alright, and now we just have to specify the flow balance constraint. And so this is very similar, or almost identical to what we did in the shortest path when the lady walked across the state. So you have to have the sum of what comes out of the origin minus what goes into the destination as a net. So starting in V, V14, put in that net. Okay, put in that sum if minus sum if formula. So in V14, here's the formula, equals. Okay, equals sum origin U14 flow minus sum destination U14 flow. Alright, so it's the same formula that we use from the shortest path model, but you want to make sure you reference the right node, which is node 1, U14. And then if you have that, we're going to copy the formula down and just get all the other nodes instead of node 1. Alright, so if you have that formula, you can double click the bottom right corner and apply it down the net outflow column. Okay, so that formula goes in V14 to V34. Okay, as you can see, the formula, all it's changing is the reference cell, the U column, and so it just references the corresponding node, 6, 7, and all the way down to U34, which is a reference for 21. Alright, and then in the required area, you want to do it just like we did before. The first one in X14 of a 1. Then you want zeros all the way in between. And the last one is a minus 1. So just to summarize, in X14 you want a 1. In X15 to X33 you want zeros, and then in X34 you want a minus 1. So it's going to sum to 0. Alright, and then the total cost is equal to the total cost range name times the flow range name, because any one you choose, it is going to choose the total cost. So in E36, it's equal to sum product total cost comma flow. So any option you choose, if there's a 1, then you got to multiply it by the total cost. Alright, so all we have to do now is run the solver to minimize total cost. Do we need anything repeated before we do that? Alright, let's run the solver, data solver. Okay, and we know that our objective, we can go find it, or I know that we call it total cost, so you can just type in TC for total cost. You want to minimize that, make sure that's minimized. And remember, in these models, we're just changing the flow column, so you can just type it in, flow. Okay, we have that one constraint, which is this one over here. Okay, you want to specify that the net outflow equals the required. So left side is net outflow. And change that to equals to, and on the right side is required. So you got V14 to V34 equals X14 to X34, and that should show that net outflow equals required. Okay, and then change your solving method to simplex LP. So your solver should look like this, and you got it. The objective is total cost. You want to minimize that by changing flow, and your only constraint is the net outflow equals the required, and your solving methods should be simplex LP. Alright, so we can hit solve if we got this. Alright, and we get a total cost of $13,575. Did you guys get that? Yeah, that's what we were supposed to get. Okay, so we chose, I'll just highlight, if you want to, you can highlight the options that the company chose to keep the machines. And so they chose to buy a machine in the first quarter and keep it for 6 quarters. So buy it in one, and then in quarter 7, they salvage it. All right, and then quarter 7, they bought a new one and kept it for another 7 quarters. Okay, and then in quarter 14, they kept it for another 7. So for a 21 quarter, they had to do something from quarter 1 to quarter 21 for their optimal machine replacement. And it turns out they determined the optimal is to basically keep it for every 7 quarters and then get a new one, because that's the point at which it becomes too costly to maintain, and they might as well salvage it and get a new one. Okay, so any questions on this one, the machine replacement? What we did here with the shortest path method for replacing machines? Okay, so that's going to wrap it up for today. And again, example 5, 5, and 5, 6, or to do next Monday, like it says in the syllabus. And yeah, so on Wednesday, we'll do example 5, 7, and then example 5, 5, and 5, 6 that we did today are due next Monday, and example 5, 7 is also due next Monday, which we will do via WebEx on Wednesday. All right, and so I'll stay on for a minute in case you have additional questions. If not, if you're good on example 5.5 and 5.6, you can go ahead and log off, and we'll see you Wednesday morning at the same time at 7:40. And so thanks, guys, and stay safe.